There we go. Okay, so we're talking about the natural number e. E is an irrational number. I'd like a reminder what irrational means. We're talking about numbers. Baron, what's an irrational number?
Number that cannot be expressed in a fraction.
Are we good with that? Yeah, simply put, it cannot be expressed as a fraction. And what do we know about the decimal form?
It terminates.
It does terminate or doesn't?
Oh, of irrational number.
Irrational. Do not terminate and they don't repeat. So, okay, so that's irrational. So the letter E, it appears as a base in many applied exponential functions. The number E is defined by that expression. The value of that as n gets larger and larger. Note E is also known as, I'll write this for you before I say it, because it may be a little bit annoying. This is pronounced Euler's constant. Euler, not Euler, Euler, because this is a German name. I feel like I've spoken about that before. And it actually isn't even Euler, it's Euler, if you're actually speaking German. But we're just going to change our vowels to be correct. So Euler's constant E. Use a table function in your calculator to approximate the numerical value of the numbers. So what we're going to do here is on your calculator, let's type in this expression. Instead of n, it's going to be x, so you're plugging in. And I had to go get the interface for the computer one more time.
Mr. Lieberman.
Yes,
I apologize if this is repetitive. Dylan Graber still has not given calculator back.
I have to use mine. COE sharing.
Oh, actually.
No. No, I can still. Yeah.
Okay, so let me see.
Okay, is the charger not here for the calculator?
Well, the one that was here wasn't working at all, so I'm looking for a new cable so it will work. So correct, I'm not here, unfortunately. I'm sorry. Make this happen. Okay. Okay, so we're gonna go to the y equals here, whatever there, and we're gonna type in the expression 1 plus. How do you do the fraction? Do you remember how to input a fraction? Alpha x. We'll make it a function. So make that 1 over x. I just type in the expression here from the package to the x power. Now we could plug in numbers if we wanted to. Could we plug in a 0?
No.
No, could we plug in a 1? Yeah, if you plug in a 1, you can see you get the number 2. If you plug in a 3, you could do a little bit of work. And what would you get if you plug in a 3? That's not 3. We would plug in. If you plug in a 2, I skipped 2. Plug in a 2, you get 1.5. The second power, which is 9/4. Nice. 2.25. But we don't want to plug in values. Let's use a table function for that. So in order to do this, I'm going to go to second table. And this is just plugging in numbers for me here.
Second graph.
Yeah, second graph table is up here.
How does it get?
Oh, can I help? So from y equals, I'm just going to the table. So 9/4, so we plug in 2, plug in 3, plug in 4. I think it's gonna start becoming decimal. Yeah, here we go. So remember, the definition of this number is what happens as these x values become larger. So how high up is this gonna go? What's that? So it's kind of a drag, and if I want to get to 100, I have to scroll down to 100. So I'm going to change something here by doing, see this function here above the window? Table set, and hit that. And instead of making the independent auto, I'm gonna make it ask. Now I'm gonna go back to the table. Are we okay with that? Back to the table and see, notice this is clear. Now if I type in a 10, it just gives me the number. Plug in.
Oh, that's good.
Yeah, it's quite nice. And so no matter what you plug in, so our question is, how big is this y value getting considering our x values? How high up is this number getting? Have some juice.
But
Do what you can.
Yeah.
Do you have a test about the science today or anything?
no,
Okay, you can go until it's gone.
Yeah.
So what number, what is this getting higher and higher and higher? Is it going to like 10 ever?
About it. Never do
Yeah, 100. Did you do 1,000 already? You typed that in, did you? So much nicer than arrowing down to 1,000, don't you think? And also one thing that's nice is if you highlight this, it will give you more numbers. 2,000, 10,000. Gonna do this. So is this gonna grow to like even 3 is gonna get there?
Each time it's going up a little.
It is going up. Go up a little bit. If I type in, can I just do like 10 to the like 50? Can I do that here? I think I broke. I can't do this. And to the, I think that it's not allowing it. It's changing it to 1. Okay, so I'll just do 1 more. It looks like there is a limit that this value is approaching, and that value is a special kind of number. It is irrational, denoted by the letter E. This number is finite number that approaches. It's very specific, and it's something you'll also study when you get to calculus. You'll learn more about it. But for our purposes here, really, all you need to know, even though we're going to look into this a little bit more, is that E is approximately 2.7. That's all you need to know.
If for us to do calculation with E, can we use 2.7?
For approximation, yeah, absolutely. Note, if you want a few more under your belt, E is also approximately 2.7. 1828. 1828. Is that going to repeat indefinitely?
Yep.
Remember, it's irrational. It's just a coincidence that those 4 repeated. After that, it's something else. Definitely not repeating 1828. But all you need to know is 2.7. And really, what we're doing here is infusing this into algebra 2 in order for you to get used to dealing with a number that you're not used to already. So we have 2 different functions on the grid here. Do you recognize what functions they are? Go ahead and discuss with your neighbor.
Is,
It's like,
the estimate.
yeah,
It's like to the, yeah.
the red one is. Three, so that's-
Yeah.
You recognize them?
Oh, yeah.
I do want to ask someone what these are. Hopefully these look familiar to you. So Emma, do you recognize what that red function is by any chance?
Like our FMS is to the X.
So 3 to the x? What made you think it's 3 to the x?
Um,
Did anyone else go through that thought process? Nice. And then the blue one?
but choose that.
What is it?
Choose that.
Are we good? Yeah, that's exactly what we're thinking of. Shoot to the x, and of course, as that base gets bigger, the graph will go up steeper, won't it? Uniju, f of x equals e to the x.
There.
Do you see where that's gonna be? We definitely know 1 point, don't we? 0, 1 is gonna be on it. Let's get one more point.
1, 2 points.
Close to 1 comma 2.7. 1 comma e, which is approximately 2.7. Right, so 1 comma like there-ish. And the other point. One over e, right? Which is approximately 1 over 2.7. Which is approximately 1/3, isn't it? And we're just rounding. And you can see that to the left of the y-axis, those values are so close that it's difficult to distinguish, but of course, it's in between here. It would also be in between here. And also asymptotic to the x-axis. This is f of x equals e to the x. Right, difficult to recognize if you just see a graph because it doesn't pass through nice pretty points like 1, 2 or 1, 3, but it does pass through 1 comma e. Any questions?
Wait, but E isn't always 0.7, right? Is it
Always, yeah.
2.25?
Oh, no, it's the limit as that x value gets larger and larger and larger. So it's yeah, so you're talking about going back to the
E doesn't always equal.
Oh, yeah. Reiterate what, thank you. Reiterate what we have here. No. Number e is defined as a value that 1 over n to n approaches as n gets larger. So it's not for any value that you plug in to this. It's as n gets larger and larger and larger. What does that value approach? So that's when I plug in that million or the billion. I was looking at the y values and checking to see the number that it approaches, the value that it approaches. So like here, there it is. That's the number that it approaches. Then you can see 2.71828, but it's not exact. I can still get closer. This is
What purpose E serve in?
that is a fantastic question. Thank you. Lots of applications in the natural sciences and economics, and we're going to be studying that in this class specifically for compound interest. And I'll bring it all together today. We'll see it today. But yeah, it's application based, right? Things that are growing all the time or decaying all the time. E is an important number. And it's definitely not as intuitive as something like pi, which is just a ratio of circumference to diameter of any circle. But this is used heavily in mathematics and sciences. So our goal today is to get used to it and to explore it a little bit. Okay, so here is a graph of a function. 1 plus 1 of x to the x. What do we notice?
Plateau.
Plateaus where?
At E.
At E. Right, that E is an asymptote to it. So this is approaching, I'll say y is approaching E. 2.7-ish. But don't worry about this graph here. You don't have to memorize what this graph looks like. All you have to know is that E is approximately 2.7. There you go. We have some transformation. So given is the graph of e to the x. Does that seem about right? E to the x. Our goal is to graph these functions. This first one, 2 times e, x minus 2 plus 1. Can you please discuss what the transformations are for a
Yeah. So if you wanted in there, yeah.
Okay. Chloe, did you get these? The transformations?
Said that. We said you have to move it up by 1 and then 2 to the left,
Up
I mean to the
1,
right,
2 to the right. Okay.
and then you would do stretch by 2.
What kind of a stretch?
A bird,
Are we good with that vertical stretch? You know it's vertical because
because it's outside.
it's outside the function. If it would have been like 2x, then that would have been a horizontal like compression thing, but it's outside the function. Perfect, thank you. So this is vertical stretch factor of 2. And how many points do I care about on this function? For every exponential function I care about 3 points. I'm going to take those 3 points and do the transformations that Chloe spoke about. Don't forget which ones come first when you talk about stretches and translations.
Right.
Stretches, anything that deals with multiplication comes first. So let's do that one. Also do B. B, don't fall for the trick. The common error. Yeah, there it is. No, this one's gonna be it.
Outside changes. That change.
Like, okay.
Yeah.
So this is that. Yeah.
You get both of them? I'll be calling someone to help me with the points. Are we ready? Dylan, can you help me with A, please?
The first thing I did was just like, move the y-intercept so I multiplied it by 2,
Okay.
so it goes up to 0, 2, and then, you move it to the right 2, and then up 1.
Are we okay with that, everybody? Oh, did I move it up? Oh, you said to the right, too, I'm sorry. The right 2 and then up like there?
Um,
Yeah, I did that right? Okay,
Wait,
And then,
wait, is there a question?
you went right to up. Oh, wait, no, but you're,
Doubled,
so you have to bring it
right
up.
2,
There's
up
one.
1. So
I can't.
this one is doubled. Doubled. The right 2 and up 1. 3 is hard. Dylan, keep on going.
and then, I took the point, negative, or like -1, I think, and then 1/2.7, and then I multiplied that by 2, so I said like approximately like 2/3.
Okay.
Um,
Just a minute, are we okay with that approximately 2/3? It's down at 1/3, so double that, perfect, so it's about 2/3.
and then I moved that to the right, 2, and then that one.
Finish,
Um,
okay,
Then final point, I said 2.7 and multiplied it by 2 to get 5.4, and then I put that over, 2 to the right, and then up 1.
and did you feel like this was enough to draw a graph? Did you include anything else besides these 3 points? But there's one more thing I want to see before we actually spin the graph,
Oh, that is,
the asymptote, the asymptote.
and then, so I said the asymptote is at, y=1.
It moves up to y equals 1. I do recommend drawing that anytime you have a function that has been moved up or down. Because otherwise you're liable to just default to the x-axis. Dylan, that was fantastic, thank you. There we go. Ready for the next one? Okay, would you please show me what this negative here does? Nice reflection over the y-axis. And show me what this 2 here does. Is it down 2? And this 1 right here. 1 to the, is it 1 to the left? How do you know it's 1 to the left?
Opposite. It's inside.
Let's be careful here.
Is it right?
What do we have to do?
You have to reflect that as well.
Yeah, the negative is an issue here. Right, that +1 is being added to the negative x. We want to see what's being. Yeah, let's factor out the negative. Exactly.
That's,
Right? Why did it make us do that? So even though we see that +1, we have to back out the negative because they're 2 different things. So this is actually gonna be moving 1 to the right. That changes things. I guess all of yours are 2 over now, like 1 in the wrong directions. So this is reflect over y-axis. 1 right and 2 down. Yeah, I'm just gonna go ahead and do this one. I like to start with 0, 1. It's such a pretty point. 0, 1 reflected over the y-axis. Stays where it is, then we move it 1 to the right, 2 down. Does that seem right? Do that, okay?
Sure.
The next one, 1 comma E, I'm gonna move to 1 comma, sorry, negative 1 comma E, and move it 1 to the right, 2 down. Does that seem about right? Do you know what the coordinates of that point are? Check, what do you check with the neighbor? What are the coordinates of that point I just drew?
Yes. Yeah, it's
Okay. Nice. Oh. There's two.
0 comma. 0 comma. About 0.7, but exactly. E minus 2. Isn't it? Isn't that exactly what it is? It was up at E. Down 2. Which is approximately 2.7 if you want an approximation. The other point,
If we wrote 0.7 on a test. That's wrong.
that is incorrect. Unless it's set to round to the nearest tenth. But if it wants coordinates of a point, it doesn't want a coordinate near that point. But for your mind, like if you're trying to figure out where it is, yeah, do the approximation, but realize it's exactly E minus 2 that I'm looking for. The last point, negative 1 comma 1 over E becomes 1 over 1 over E. Did you already place this one? Go ahead and write the coordinates of that last point. That. I'm gonna call someone to get the coordinates of that point. And I'll tell you that the x coordinate is 2. I'll give you for free. You check with your neighbor already? I want the y coordinate. Okay, so Josh, did you get this one?
I'm not really sure.
Let's talk about the coordinates here first for this one where we started. Do you know what these coordinates are?
1 over E.
Yeah, negative 1 comma 1 over E. So the 2, right, when you flip that over the, you flip this over that y-axis, move it to the right 1, then down 2. The x coordinate is pretty simple, isn't it? Right, that's
Oh yeah.
So let's follow this. Let's just follow the path. First thing this did was it went over here. Right here, the y coordinate is. Oops, yeah, that's right. 1 comma 1 over E still, isn't it?
Yeah.
Okay, then we move that to the right where it's 2 comma 1 over E. And then what happened after that?
Oh, is it 1 over E minus?
Is it 1 over E minus 2? Exactly what I'm looking for. Thank you. One over E minus 2. And of course, I also should graph in the asymptote, which is y equals negative 2, just so we have a floor. It's like a skeleton for your model. Do I have a point right here? Yeah. Something like this. Did I do that right? think so. Remember, if they're not forming an exponential curve, if it's forming like an N or something, or a strange shape, please make sure you fix your mistake. Okay, let's do some applications. Insatiable killer. Oh, is there a question before I move on? That's the reputation the gray wolf acquired in the United States in the 19th and early 20th centuries. Although the label was undeserved, an estimated 2 million wolves were shot, trapped, or poisoned. By 1960, the population was reduced to 800 wolves, starting at more than 2 million. Wow. The figure at the right shows the rebounding population in 2 recovery areas after the gray wolf was declared an endangered species and received federal protection. The exponential function f of x equals all that models the gray wolf population in Western Great Lakes, f of x years after 1978. So A, according to model, what was the gray wolf population around its nearest whole number in Western Great Lakes in 2018? So this is according to the model. So go ahead and figure out how to get that. See if you use your calculator to do it.
Right? Your son.
Either-
Yes, that's fine. So, what was that you I can.
No, there's a function, so there has to be something.
Okay, did you get that?
No. It's.
Yeah. Oh, did you find the E on your calculator? Make sure you're not using an approximation, use the actual E. Where is it? Above division, thank you. So you have to hit second division, is that what it is?
Oh. But you missed.
I think there's a one that may be more appropriate.
Oh.
Give us a number.
It's it.
Are we writing that number down?
To get four.
For A?
Yeah.
Well, you're plugging into this function. You're plugging some number into this function. Do you see where else E is on your calculator aside from above the division sign?
With e to the x.
There's E to the X above the,
In.
is that in?
Yep.
Wait, is that an in button? Is that an ln?
Nope, that's an I.
It definitely looks like in. And it's ln though.
That's stand for.
Natural logarithm. Which we'll be doing soon enough.
But then shouldn't the n come first?
You're correct. It's from the French. I know.
Okay, that's all right.
Did you get it? What number are we plugging into this function? Plug in what? Plug in 40? 41? Well, it's in 2018, right? And it's after 1978, isn't it? So how many years is that? Is that 40? So you're gonna plug in a 40. So it's F of 40 is equal to 1144 e to the 0.0325 times 40.
Yeah.
So what did we get?
Oh, it means the function model, not the graph.
Got the function model. And we're just plugging it into that.
Oh,
Exactly, and we're gonna check to see how it compares. So approximately, what, 27,000?
why are we finding it at the 40 though, when it just? Cause
Yeah, the model is just good after 1978. So this is we're talking about 2018, right? Plug-in 1 would be 1979, plug-in 2 would be 1980. 40 is 2018. How many thousand? 4,197.7. Should we round
oh,
to the nearest whole number? Let that last one live.
you could,
I don't know. It's just a model. It's math. It's not like life follows that rule. It's just a way of estimating. And that would be wolves. Specifically gray wolves in the Western Great Lakes. Does the model underestimate or overestimate the gray wolf population of the Western Great Lakes in 2018? Overestimate or underestimate?
oh,
Well, the actual is 4222, so it's an underestimate. By, let's see, 422 minus 4198 by, what's that, 24 wolves? That's not bad.
yes.
Any questions? Again, population is it's a huge application for E. Compound interest. Would you please discuss what you know about compound interest from your previous classes?
Yeah. Like it's interest that's like gonna go up. Right? Oh, yeah. It's like, put something in. Yeah. I feel like, maybe, yeah, it like, it's interesting. Wait, I don't even know yet.
Okay, so compound interest, without formulas, just what is compound interest? Do you know? Hey, Barry?
It's like when you invest money and then get interest, and then the next year's interest includes the interest of the previous year.
Perfect. Are we good with that? That's as opposed to
The other one, where
the other
you
way.
get the interest based on the initial and nothing further.
Exactly, that's called simple interest. Where let's do like a simple example, like, and I just have a sheet of scratch paper here. Let's say you start with $1,000 and 10%. You get 10% interest per year. So if it's simple interest, that means the first year you're gonna have 1,100, the next year you're gonna have 1,200, 1,300, etc. Nowhere works like that. Banks do not work like that. They do compound, which means after 1 year, you're going to have $1,100. The second year, how much more are you going to have?
Well, then,
You have 1,100 plus the 10% of that. Like Baron said, 1210. Does that make sense? Next year, you're going to have
1321.
1210 plus, yeah, 1331. So when you compare that with simple interest, you can see it's more beneficial. Yes,
Wait, sorry, just clarifying, where did you get the 121 from?
good question.
Percent of the 12.
Oh, so you take 10% of the thing.
10% of the money you already have. It's simple, it's just 10% of your original, 10% of this every year. Doesn't happen. They acknowledge you have more money in the bank, or if it's a loan, you owe more money. They see that and adjust it proportionally. So that's why that 1,100 is increased by 110 rather than 100. giving us this much, and then the next year you have 1,210, you add 121 to it. At the end of that year, you would have $1,331. Are we good with that? So that's the idea of compound interest. So let's go back to the packet. So just for 1 year, this would be P. Let's see. Suppose a sum of money called the principal is invested at an annual percentage rate R in decimal form, compounded 1 per year, because interest is added to the principal at year's end. Cumulative value is P plus the interest, P times R, which could also be written as P times 1 plus R. Does that look familiar?
No, but
If it doesn't, that's fine. So that just means after 1 year, we have the amount that we have is P times 1 plus whatever the rate is. In the second year, we're gonna have the previous amount times another 1 plus R, or P times 1 plus R squared. The third year, you see what's gonna be? You have the original amounts times 1 plus R to the third power, dot, dot, dot. So after T years, oh, that should be an A, this should be a P. P times 1 plus R to the T. Any questions? Yeah, I'm gonna give you just 3-4 minutes. I'll start again at 10:20. Just zone out, stretch, whatever you need to do. Okay. Moving on. I go back to the scratch paper. Now, there's something a little bit strange about these problems in that this is compounded yearly, right? Just at the end of the year, they're like, okay, here's 10%. At the end of the next year, they had, here's 10% of what you had. But how about all that time in the middle? Hasn't your money been in the bank that whole time? Why should you just get that reward of interest at the very end of the year? So what would happen if it's compounded like every 6 months? Instead of waiting the whole year to get 10%, what if after 6 months you got 5%? And then the next 6 months you got
That would be better.
5%. Would that be better? Investor?
Yeah,
Yeah, let's see what would happen after 1 year if it's compounded every 6 months. Let's see, we start with 1,000. Then after 6 months, that would become, we get 5%. Okay, so 1050, and then after 1 year, you get 5 more percent. What is 5% of this? Could you discuss with a neighbor how to do this without a calculator? How could you get 5% of this?
Okay.
Okay, so who can help me? Am I gonna, I don't want to use my calculator. How do I get 5%?
chop to 0 off divide by 2.
Are you good with that? Get 10% divided by 2. So in our minds, we go 105, which becomes
52.
52.5. Are we good with that? For 5%? 10%, I love chop the 0 off. That's divided by 10. Cut it in half. So it's gonna be that 1050 plus 5250, which results in, what is this? Is that pretty easy to add? We could compare that to if it's just compounded 1 time. Right, compared to this. It's a little bit more in our benefit, isn't it? So that's the way banks actually work. They don't just compound once a year. So most savings institutions have plans in which interest is paid more than once a year, right? Interest is paid more than once a year. Compound interest is paid twice a year. The compounding period is 6 months. We say the interest is compounded every 6 months. It's compounded semi-annually or semi-annually. When compound interest is paid 4 times a year, the compounding period is said to be compounded. That one's quarterly. Some plans allow for monthly compounding or daily compounding. In general, when compound interest is paid n times a year, we say that there are n compounding periods per year. So we're gonna have to adjust this formula, aren't we? This formula is just when it's compounded yearly. So what happens is that P, what does the P stand for? Principal, that's the starting amount of money. So we're going to take that rate, and remember what we did with it? We're going to divide it by however many times we're compounding. Divided by n. But now we have to keep in mind that it's n times per year, so we're going to raise it to the n times t. In other words, if it's compounded monthly, that n is going to be 12. Does it make sense that we now have to raise it to the 12 times t? It's no longer once per year. You had to multiply by 12 times per year. And this is a formula that you do have to know for sure. Some banks use continuous compounding, where the number of compounding periods increases infinitely, such that it's compounded every instant. Every instant. This results in the formula A equals P times.
There's no way banks actually just
They do it. Results in this formula. Does that number look familiar? E. And you can see hints of the definition of E in the formula here. Remember, E by definition is that 1 plus 1 over n to the n as n gets bigger. As n goes to infinity. So the biggest application that we will be dealing with is when it comes to money, called continuous compounding. So you invest, and that's another formula I have to remember, by the way. That was nicer, isn't it? It's such a pretty little formula. You invest 5,000 into an account that pays 4.5% per year, compounded continuously. How much would you have after 10 years? I'll give you a minute to figure this out. We just do both of them.
Here, or continue. Oh, it is. Oh. Yeah, one plus one over. Then, okay, then. Should I have it? Is that
Yeah,
That's
we know.
You get it?
yeah.
Did you get them? Okay, I see. Brandon, can you help me with this first one?
Okay, so I said A is equal to 5,000 e to the power of 0.045 times 10.
Are we good with this? Thank you for changing the decimal, by the way. That would be a crazy number if you input 4.5. And what do you get in the end?
I got 7,841.56.
5.6. Does this match what other people got? Now, notice we start with 5,000 and it is increasing at 4.5% for 10 years. So if you got something like 900,000 or $60, please make sure you figure out your error. It should be like, it should make sense. Like, should be selling more than 5,000. Like, to me, 7,000 makes sense. 4.5 years. Did anyone else get that same number? You got that same number? Okay, so we got a couple other people getting that number. Make sure you could do that in your calculator. And which is the E that you're using?
The one above the division.
You could use the one above division, but I recommend using the one above the other side, the LN, or the one that looks like IN. Yeah, Dylan?
It's like, for this, can you use the A equals P parentheses, 1 plus R minus B?
If it's compounded continuously,
Anyway, yeah.
Yeah, thank you.
That's an annual.
It does say per year, but that 4.5 is being divided into an infinite number of pieces when it says continuously, so you must use P times E to the RT. Yes, Deanna?
For the first formula, why didn't you raise it to the n times t power? Why wouldn't it just be t?
Good question. Think about the example I said with the 10%. For 1 year, how many times, if it's compounded every 6 months? Didn't we have to do the calculations twice in 1 year? Because it was divided by 2. So whatever you're dividing by has to be, you have to account for that in your power. So is it right? I want to make sure that you're getting that number. As a kid, when he told me that 5,000 times e to the 0.045 times 10 is exactly what I'm looking for. Can I help with anything? Okay, the next one, I need a formula and then I need your number. Compounded monthly. Lily, can you help us with this one, please? For compounded monthly. Oh, did you not get to this one yet? I'll give you a moment to finish this one. Compounded monthly.
So I think that one's right. That
I thought monthly is like, well, but I thought that's the year, it's in terms of name. Both ends. No, wait, I don't. What was the argument? 7,008. So now. Everyone's saying that, guys, isn't it anything?
Oh, yeah, so. Or 20, right?
Did you get it?
That's not
Okay. So you've had some time to work through this. Lily, can you tell us the equation you used to compute this, please?
Yeah, so A equals 5,000 times 1 plus 0.045 divided by 12, and then raised to the power of 12 times.
Are we good? Think about it, it's 10 years. It's compounded monthly. Does it make sense? It has to be raised to that 120th power. Every year, every month, getting a little piece. And what do you get when you calculated this?
I got 77,834.96.
34.96. I guess we don't need approximations here since it's money. We can say we're going to get exactly that %. Do we agree with this? Did you get that number?
Yeah, but that.
Yeah.
Oh.
So are we surprised that this number is less than the continuously compounded interest? That's our benefit to compound more often. So Lily, do you get the difference here? Do that calculation here.
$6.60.
$6.50.
60.
60 cents. Difference is. Okay, is it a big difference? No. It's a difference though. If it's instead of 5,000 or 500,000 or 5 million, that would be more significant, but it is different for sure. Thank you. Okay, a couple of last things before we go. If 2 to the x equals 3, what is 4 to the negative x equal? This is a little bit of a trick problem. I'm gonna give you a chance to think about this, but my big hint is it's not asking for x, it's asking for 4 to the negative x. So see if you could figure out how to figure out what this equals. Any ideas? Okay. Well, what's the relationship between this 2 and the 4? And it's not a coincidence that they're related. 4 is double. In other words, I can rewrite that 4 as 2 squared to the negative x, can't I? Which is the same thing as 2 to the negative 2x, is that correct? I'm just going to play with this a little bit. So I have 2 to the x to the negative second power. Can we agree that all those are equivalent? This is a negative second power. So all I'm going to do is I'm going to take the first equation and do what to both sides? And raise them both to the negative second power. Right, if I start with this, raise to the negative second power. Don't I have 4 to negative x on the left? And on the right, I have. Check with your neighbor, what is 3 to the negative second power? You know what, I want to hear it on the count of 3. 1, 2, 3. Good, it is 1, 9. Are we good with that? It's a little bit of a trick. Don't try to solve for x. It won't lead to happiness. And finally, find the exponential function with the horizontal asymptote y equals -3, whose graph contains these 2 points. Where should I even start with something like this? How about with a graph? Does that make sense as a place to begin? Let's graph it. I'll put this on the side so I could do a little bit of work. Y equals -3, that is down here. 1, 2, 3. Y equals -3. We have a couple points on this, 0, -2. And -2. Is this enough? It's definitely enough. I'm going to guide you through here. Normal exponential functions are y equals b to the x. This one's going to be b to the x -3, isn't it? For sure, it's -3. We know that because that horizontal asymptote is a y equals -3. So our goal is to figure out what is b. Should I use slope formula for this? Please only use slope formula for linear functions. Give me a moment to figure out how are we going to get b.
Yeah.
You getting anything? Okay, so notice at this point, Doesn't help, does it? Did you try plugging that in? Because all we want to know is how big is this growing or decaying? So that point, that 0, 1 doesn't help. We want to know the other. You plug that in, let's just see what happens. The y value is 1, the x value is -2 minus 3. So what do you get? B to negative second equals 4, is that right? Did I do that right? And now what? How do I solve for B?
Use both sides.
Thank you for using algebra. Yeah, you raise both sides to the, well, 1/2 to it. We want to cancel, we want to isolate the B, so I'm going to raise both sides to the -1/2. That leaves us on one side with B. What is 4 to the -1/2? Would you please discuss with your neighbor?
Oh, okay. It's
Would you please show me your answer once you have it? You may have to use both hands.
I don't know what, like, and then negative, which root, so yeah, like square root of B. Okay, I don't want.
I'm seeing negatives. Is there a negative number involved here? Who could talk us through this? 4 to the -1/2. How do I do this? The -1/2. So your rule of exponents, you know that negatives mean it's gonna be 1/4 to the 1/2. 4 to the 1/2 is the square root of 4, which is 2 on the bottom, 1/2, 2. So our function f of x equals 1/2 to the x minus. Is that 1/2 a surprise? Or the fact that it's between 0 and 1 is a surprise? Not a surprise because you can see that this exponential function is decreasing, which means that b is going to be between 0 and. We take a few minutes to check in with your neighbor. What are the main takeaways for today's class?
Yeah. Like last,